Well, greetings and welcome to Nani Notes. Here we are on lesson 1.5 in our McGraw Hill text. And before we start this time with the practice questions, I want us to go back to page 30. Just want to emphasize something. Yeah, this construction where we said construct a line perpendicular to L, passing through the point C, which is already on the line. Now, we looked at it and your textbook shows it with a three circles like this. And I mentioned that it's okay to do arcs. I used to teach it before. And of course, if we did it this way, and then we would just construct the two, swing the two arcs until we got this intersection here, we would have right there, 1, 2 points, which define a unique line or a segment. It would be unnecessary to bring in a straight point. But I guess for mechanical reasons, I guess having 3 points, which should be collinear, may help us come up with a smoother drawing. But I would accept either of those as constructions for this line perpendicular to a given line through a point on the line. So I'll ask your teacher. And enough of that. Let's have a look at this one. Oh, yeah. This was actually kind of fun. You guessed where the point would be, and then again you reviewed your compass construction. And if you remember the way we did this, and we did this before, we did this in the intro to the class. First swing, random. Second swing, well, we're going to gap from one intersection to the other. And I'm going to swing an arc. And there I go again. I reverse the compass. Of course, the second and third compass will have the same setting, or the same gap, if you will. That's going to give us this point, this intersection, and then with our straight edge. And look at that, our guess wasn't so far off. So that again was the angle bisector construction. I know if the textbook shows the three circles, which is okay. You know, personally, I find it confusing because I know a lot of folks are drawn to this intersection down here, which could be. I mean, sometimes it's, well, let's see. Hang on a second. Let's do this. Let's pull this out and see what happens. See, now that intersection is on the other side of the vertex. I guess technically it still works, but this is the one, this right here, this is the point I like right there. Okay, enough of that. Let's get back to the exercises. Now, this question in this diagram, oof, boy, I like to be thorough here. We're constructing a perpendicular through this point C. Why was it necessary to make this circle? Well, I'll give you an idea to visualize it. Let's take it out. Take it out. What have you got? Huh, look at that. If I remove that first circle, really, and what I've got here is the perpendicular bisector construction. So imagine, if you will, all you did was you took this point right here, and you made a segment by making this the midpoint of the segment. You made a segment, you cut it out, and then you executed the perpendicular bisector construction. Well, that's the way I see it. I mean, your explanations, I'm sure, will be similar. And again, if you were constructing or swinging arcs rather than full circles, maybe it would look a little bit more like that. Enough of that. Now, boy, this honestly, this makes me dizzy just to look at it. It makes me cringe a little bit too. This whole thing, EF. The line is. I was always taught that an angle bisector is a ray, but maybe I'll compromise and say it's contained on the line AE or EF, and yeah, I guess that's going to work. So they're looking at it. See, they're looking at these two. It's the same construction, like the perpendicular bisector construction. So you're looking at EF being a line. So I can see why they're saying that. And that does work. It's the angle bisector of BAC. As some famous Alaska politician once said, you betcha. So yes, BAC, this cuts it in half, guaranteed. Now, EF is a perpendicular bisector of BA. What? BA is over here. Do these two look perpendicular to you? I don't think so. EF is the perpendicular bisector of AC. Wait a minute. This is getting crazy. EF is over here. Well, that's just as crazy. And EF is a perpendicular bisector of BD. Now, here's a tricky one. Because we don't have the segment drawn in, but you can imagine if we did draw that in. Let me change that, make that a little, make that thick. And if you turn this on its side, heck, this is, and you focus on these two swings, that is the perpendicular bisector construction. So in this case, the line EF would be indeed the bisector of the segment BD. That was probably the trickiest one that I've seen in many of these in these sections here. Now EF parallel to CD. Hey, well, EF, CD. Well, two lines that intersect, and especially, well, two lines that intersect are definitely not parallel. So the only one that's true, that one's true, and that one's. So the only two that are true, right there and there. A, alpha, delta. I like that. Okay, let's move it on to the next page. Next page. Okay, 34. Now again with the rhombus, you know, we're identifying using words that we've never identified, but I'll go with it. I guess we're saying it right now. It's a quadrilateral with four congruent sides. So how do we know it's a rhombus? And I know your explanation would contain something of the following. I'm sure you would mention that. So if this is the radius AB, then AC is equal to that radius. And the same, and grab it the right way. And the same goes true for AD. The same logic can be extended to the other side. But I can't grab that one. So let me just animate it like that. All four of those are represented and equal to the distance AB, which is the radius of circle A. It's the radius of circle B. Nice. Now I'm not, well, I'll bring up that word later on. Hang on. I'm going to bring it up on this one. We have a vocabulary word that I've just been dying to say. All right, so we've got the centers of these three circles. Which line segment is congruent to HF? HF starts over here, ends over here. Now we've seen this argument before. I know, for example, that AB is the radius of circle A. It's also the radius of circle B. That makes these two circles congruent. They have the same radius. I've used that same logic before. AC is the radius of circle C. It's also the radius of circle A, meaning these two circles are congruent. The same logic can be used here. CB is the radius of both these circles, C and B, so those two are congruent. Now, I'm going to mention this because you have seen this in Algebra 1. You have seen this statement before. And actually, I mentioned it in class, and some of you finished the statement for me. If A equals B and B equals C, then A equals C. That, in, let's say, in algebra or in arithmetic, that is simply known as the transitive property. And we're going to be exploring the transitive property in geometry. It comes up a lot. So, I hope I didn't overstep here, but You are going to see that, and even if you, gosh, if it doesn't come up in this text, you've already been using it. You know it. So let's look at HF. HF is a diameter of circle C. So the diameters of the other circle, FD and HD, would certainly be congruent to HF. Wait a minute, which line segment is, did it really say that? Or did it say HF with a, no. My eyes aren't as good. I think that says HF. Okay, well, we better move on to the next page. All right, you take your patty paper. We did this in class. Make sure, well, and if you were absent, maybe you didn't do it. And we've done it with an angle as well. Explain why the crease is the perpendicular bisector of AB. So let's simulate this. You've got your patty paper, and maybe this will be on your little quiz. I've got a segment drawn on it, and then I fold my paper very carefully. I'm going to fold it in half, like this. I'm holding it up to the light, and I'm putting that A, so it's right on top of the B. I hold it up to the light, and I put a crease in that paper. And right there, I'm thinking, hey, that looks like the perpendicular bisector. Why? Because the set of points that are equidistant from A and B. When I fold it in half, I put the A on top of the B. That distance is halfway in between. Pretty nice, huh? Okay. Now, in this diagram, it says CD is the perpendicular bisector. Oh, again, they're saying segment. I prefer to say a line CD. You can say the segment CD contained in the line CD. Perpendicular bisector of the segment AB. Assume the conjecture that the set of points is equidistant from A and B is the perpendicular bisector. Is point M closer to point A or to point B? Or is it the same? How do you know? Well, we just said that the conjecture, I'm going to put a random point here. Watch this. I'm just going to go from A to a random point right there. Now, our conjecture says that this random point right here is equidistant from A and B. So I'm marking it with these tick marks. Whether I slide it up here or I slide it down there. If I slide it all the way down there, what happens? It's no mistake they chose M because M stands for midpoint. I like to think of it as perpendicular bisector. It's simply two words, perpendicular, which you see right here, and bisector, which you see with those tick marks right there. So there you go. That is a perpendicular bisector. So M is certainly the midpoint or equidistant from A and B. All right, one more page and we're almost done. All right. Now, this is interesting because for once, we've got two different size circles and different kind of construction. And we know that, well, maybe we'll see in the future, we'll call this thing a kite, ACDB. But that's not the question right now. They're both centers of the circle. Explain why the length of segment CB is the same as the length of segment CD. Well, that makes a lot of sense because, again, let's just draw in. I'm just going to draw in a random segment right there. What it comes down to is that CB is the radius of circle C. And that's the same. CA is also a radius. CD is a radius. So all three of these are congruent because they are radii of the same circle. The only thing different in this diagram
is that the other circle, these two circles are not congruent because circle B does not pass through C. So this is not a perpendicular bisector construction. It's an interesting construction, but it is not perpendicular bisector. And there you have it. We've got 3 congruent segments there. And well, I hope this is helpful, and we'll see you all back in class. And again, thank you for watching 99.